right. 4.3 was about graphing quadratic functions. Number one, how do you recognize a quadratic function by looking at its equation? Second degree, or the highest, the variable with the highest exponent is x squared. And number two, you know what the equation looks like. What does the graph look like? A parabola. The leading coefficient determines the concavity. How do you find an x-intercept? All right. To find the x-intercept, you let y be 0. To find the y-intercept, you let x be 0. If you have a concave down parabola, what is the vertex going to be? I'm not asking for the coordinates of the vertex. I'm referring to relative extreme. Yeah, it's going to be a maximum value. If you have a concave up parabola, then its vertex is going to be a minimum value. What's the domain of any quadratic function? Domain is what x can be. So what is it for a quadratic function? All real numbers, or you could write negative infinity to infinity. All right, that was our warm-up quiz. Today we are graphing higher order polynomial equations, polynomial functions, not only equations that have x squares in them or x cubed, and we've really already talked about x cubed and negative x cubed, but we're going to graph fourth, fifth, sixth degree functions. What I really like about this section is the fact that when I was in high school, I didn't see the big picture. I'm not sure the big picture was told to me. It may have been and just went in one ear and out the other. But I felt like I had to make a huge XY chart to graph anything because I didn't realize what all graphs have in common. So I'm making sure that you know what all graphs have in common. Real quickly, graph those first four for me. That should take you 10 seconds because I'm talking rough sketch. All of those were in your library of functions before you took the last test. X squared is a concave up parabola. Negative x squared is a concave down parabola. X cubed is that ascending or increasing snake shape. And negative x cubed is that descending or decreasing snake shape. Well, it turns out the end behavior of the graph of any polynomial function is determined by two things: the sign of the leading coefficient and whether the degree of the polynomial is even or odd. Those are the only two things you have to know about any polynomial to know at least what's going on the ends. These are really the only things that can happen on the end. Either both ends go up, both ends go down, it goes down on the left, up on the right, or up on the left and down on the right. That end behavior is determined by whether the leading coefficient is positive or negative and whether the exponent, the highest exponent, is even or odd. It turns out that any even degree polynomial with a positive coefficient pretty much looks like x squared. So this could be x to the 6th or x to the 8th or x to the 22nd. The higher the exponent is, the faster your y's are going to get big, so the more narrow it will be. But if you're not using graph paper, you can't tell the difference between y equals x squared and y equals x to the 4th. If it's even degree with a positive coefficient, it's going to look like x squared. If it's even degree with a negative coefficient, it's going to look like negative x squared. So this may be negative x to the 6th instead of negative x squared. It's going to go down on both ends. If the degree is odd and the leading coefficient is positive, then it pretty much looks like x cubed on the ends. It's going to go down on the left and up on the right. And if the degree is odd and the leading coefficient is negative, it's pretty much going to look like negative x cubed. It's going to go up on the left and down on the right. That would have saved me a whole lot of time in high school, just realizing that's all I need to look at to get the end behavior. So f of x equals x to the 6th. I make this multiple choice, A, B, C, or D. What does x to the 6th look like? Even degree. And a positive coefficient means that both ends go down just like x squared. It's steeper than x squared, but if I don't have graph paper, you're not going to be able to tell that. Does my example B, f of x equals negative x to the 5th, look like A, B, C, or D? Yeah, it has an odd exponent and a negative coefficient. So it's kind of going to look like negative x cubed. Only steeper, but if you're rough sketching, you can't tell that. That's pretty powerful. That gives us a lot of information about a graph. The other information that we need to get a better graph is what we already know about horizontal and vertical translations. Whatever is added or subtracted inside the parentheses, that's your horizontal shift, and your horizontal, yes ma'am? Gosh darn it. I think I said it would look like x squared, and then I drew negative x squared. Just to see who was paying attention. Just to see who's paying attention. Just to cover my butt on the video recording of this. No. No. I've started telling all of my classes now, I will either say what is right or I will write what is right. It is your job to figure out which. There I said what it was right and wrote what was wrong. I'm sorry. Thank you for telling me. Don't ever let me get away with that, because it's just, yeah. No, you thought you understood until I did that. Nope. I said looks like x squared, and then I drew it down. Joe know why. This one's right, though. Negative x cubed goes downhill from left to right. Negative x to the 5th will go downhill from left to right. All right. Where were we? Whatever is added or subtracted inside the parentheses before the exponent is applied, that's your horizontal shift, and your horizontal shift has always gone the opposite of what you might have guessed. And whatever's added or subtracted after the exponent is applied, that's your vertical shift, and the vertical shift acts like you would think. Adding something moves the graph up, subtracting something moves the graph down. So apply that to what we've just figured out about end behavior, and let's graph these two. This is going to have the same end behavior as which one, A, B, C, or D? It has odd degree with a positive coefficient. So it is going to look like C going uphill from left to right, except for its, in calculus, we'll call that inflection point. Here we're just calling it the critical point, or in a really off moment, I might call it the snake's belly button. What is that critical point? Instead of 0, 0, how's it been shifted? 4 to the which direction? Nope. That horizontal shift always works the opposite of what you expect. So that horizontal shift is actually 4 to the left. Your vertical shift is down 2. So what's your turning point? Instead of 0, 0, it's -4, -2. Now, if I wasn't writing stuff down so you could copy it and have it in your notes, I wouldn't even need to write that down. I could just look at it and see that critical point, -4, -2, and then attach the end behavior that I know that function has. I know it goes down to the left and up to the right. Just like x cubed. By the way, on the test, I had some pretty goofy looking graphs for x cubed. The snake is not all coiled up. I had graphs that looked like this. No, not really. As a matter of fact, that's not even a function. If I can put a vertical line anywhere on that graph that touches the graph in more than one place, that's not even a function. So be a little bit more careful with your x cube. It's pretty smooth. It turns right here, but other than that turning point, it's pretty smooth. What about example B? Is it going to look more like A, B, C, or D? Which one? B, because it is even degree and has a negative coefficient, this negative coefficient right here. That tells me both ends are going to go down. Where is this turning point? Yeah, because isn't this the very same thing as negative x minus 2 to the fourth plus 1? Is that the same thing? As long as I keep the x minus 2 to the fourth with a negative coefficient and the 1 having a positive coefficient, it doesn't matter in what order I write those. So that 1, even though originally it was written in the front, it's your vertical shift. So what is this point? Positive 2, opposite of the guy in parentheses, and the guy on the end, positive 1. So that critical point is 2, 1. Ooh, let me show you why that would be highly illegal. Just so you'll know, if I had 2 times x plus 2 squared, for example, I can't distribute that 2 until I take care of the exponent. The order of operations is exponents before multiplication. You could FOIL that out and then distribute the 2, but you couldn't distribute the 2 first. And for the very same reason, you couldn't distribute that negative before you evaluated the exponent. All right, so we're quick sketching here. The turning point or the critical point is 2, 1. And it looks pretty much like a concave down parabola, although the word parabola is specifically saved for a quadratic equation. This isn't a quadratic equation, it's a 4th degree equation. Any questions? We just about have this down. We know the end behavior. We know how to tell if the graph has been shifted left or right. Let me see what this 24 to 36 even is before we talk about my note number 3. Page 340, 24 to 36. This must be the old edition. No, this is the 9th edition. Page 340, 24. I don't know what that, we don't, maybe I need to update the handout. I have the wrong page number, but I think it's 27 through 39 on this page, and it's just the graphs we've already done. This number 35, this odd degree function with a positive coefficient, it's going to look like x cubed, but what's its turning point going to be? Positive 1, positive 2. This number 40 is like the one that we just did in that you can turn it around and write it negative x plus 2 to the fourth plus the 3 on the end. It's still 4th degree negative coefficient. So what are both ends going to do? Both ends going to go down, and its turning point is what? -2, 3. So I think I have the wrong page number and maybe the wrong problem numbers, but after the 2 examples we just did, you should be able to do 27 through 40. All right, so let's go on to my note number 3. A polynomial of the form a sub n, and when I'm saying a sub n because n is a subscript, a sub n x to the n plus a sub n minus 1 x to the n minus 1, on and on and on down to some constant. That's kind of scary looking, but that's just an nth degree polynomial in descending order. In descending order, there's a constant on the end. So an nth degree polynomial in descending order still has the same end behavior as determined by the first term. In other words, it doesn't matter if you have 5x to the third plus 9x squared minus 6x plus 14. To determine the end behavior, you only have to look at the leading term. That's what note 3 is saying. All the other terms can give you squiggles in the middle. Instead of being a nice smooth graph like this one was, we may have one that actually looks like that, as long as it passes the vertical line test. Now, we're never going to have one that looks like this because that's not a function. Note number 4 tells you how many squiggles in the middle can happen. A polynomial of degree n has at most n minus 1 turning points. So in other words, a 5th degree polynomial can have at most how many turning points? 4. A 7th degree polynomial can have at most 6 squiggles in the middle. All right, that's what note number 4 means. Now we're going to start graphing just a little bit more precisely. And here's what I want you to do on your homework, and I want you to be so meticulous about it that I've actually made you a page that you need to print on Momentum. This is the second half of your homework. There are a few problems that you do on MyMathLab, and then you print this handout. I have it typed on the back for you. You do assignment 13, and you do these problems from Momentum. And all of these problems look just like the examples that are on your notes for today. All right. Here's what we're going to find for every polynomial that we graph for homework. Number 1, or letter A, we're going to determine the end behavior of the graph. Basically, on the ends, does it look like x squared, negative x squared, x cubed, or negative x cubed? That is still determined by whether the degree is even or odd, whether the leading coefficient is positive or negative. In part B, we're going to find the y-intercept. How do you always find a y-intercept? Let x be 0. In the C part, we're going to find the real zeros of the function. Now, we've never used that term real zeros before. We have used the word x-intercepts before. How did we find x-intercepts? Let y be 0. Isn't that the same as set f of x equal to 0? Because y and f of x are the same thing. When you set a function equal to 0, you may get real solutions. You may also get imaginary solutions. You might get solutions with an I in them, and you can't graph those imaginary numbers. So the term real zeros refers to the solutions to this that are real, just the real numbers. The real zeros of a function are the same as its x-intercepts because you obtain them by letting y equal 0. The real zeros of a function are where it crosses the x-axis. Determine whether the graph touches or crosses the x-axis at each zero. We need to talk about another word here, multiplicity. If x minus something to the nth power is a factor of this function, if I set x minus c equal to 0, x minus c equal to 0, and solve for x, what would x equal? C. You just add c to both sides and x equals c. So if x minus c is a factor of the function, then c is a 0 of the function. This is saying if x minus c is raised to a power, that power is called the multiplicity of that 0. Multiplicity always refers to the exponent. So if you have x plus 7 to the 5th, what's going to be one of the x-intercepts of that function? X plus 7 to the 5th. If you set x plus 7 equal to 0, what do you get? X equals negative 7. Negative 7 is going to be one of the x-intercepts. And then the multiplicity of the x minus 7 to the 5th is just the exponent, 5. So whenever I say what's the multiplicity, I'm saying what's the exponent of that factor. And that's important because it tells you whether the graph touches or crosses the x-axis at that 0. Let me read the last time. We'll look at this picture. If that exponent, if the multiplicity is even, the graph touches the x-axis but does not cross, you could even make a note there, does a U-turn. As is the case right here. I don't know exactly where that graph is touching the x-axis, but I can see that it comes down, it touches but does not cross the x-axis. It does a U-turn at that 0. What I know about that factor is that its exponent was even. If n, the exponent, is odd, the graph crosses the x-axis at c. So right here where the graph crosses the x-axis, this x-intercept, I know it came from a factor that had an odd exponent. So even exponent, the graph's going to touch and do a U-turn. Odd exponent, the graph's going to touch and cross the x-axis at that point. That'll make more sense when we see an example, which is exactly what we're ready to do. This is what the page that you're going to print off momentum looks like. And this is exactly what a problem on the test looks like. F of x equals x times x plus 2 squared. Now be careful when I ask you for the exponent of that polynomial. Don't forget that this x has an exponent of 1. And if you FOIL this out, you'd have an x squared. So you'd have an x squared times an x to the first. What degree would that give you? Yeah, that's a third degree function. Because if you FOIL this out, you'd have x squared, and then you'd have to distribute this x, and you'd get an x cubed. So that's a third degree function with a positive or negative coefficient. If there's not a negative out front, then it's a positive coefficient. Does that mean it basically looks like A, B, C, or D here? Yeah, C is odd degree with positive coefficient. It goes down on the left and up on the right. So what I'm asking you to do on the homework is just make a little note. The ends look like that. It may have some squiggles in the middle. As a matter of fact, I know that it has no more than how many squiggles in the middle? 2, no more than 1 less than the degree. This may have 2 squiggles in the middle. But when I ask for the end behavior, I'm asking for this little picture. How do you find the y-intercept? Let x be 0. 0 times 0 plus 2 squared would be what? 0 times 4. 0. So this graph touches the origin. It has the ordered pair 0, 0. How do you find the zeros of the function, also known as the x-intercepts of the function? Let y equal 0 or set the whole thing equal to 0. That's saying the same thing. If you set x times x plus 2 equal to 0, what two solutions are you going to get? Yeah, x equals 0 or x equals -2. Those are your two zeros. Just because I left 3 blanks doesn't mean you're going to have 3 zeros. I just wanted to cut and paste all these boxes the same. Is that okay? All right. What is the multiplicity of the 0, 0? Or what is the multiplicity of the x-intercept at 0? What is the exponent of that factor? 1. And based on the fact that this has odd multiplicity, I know whether the graph touches or crosses the x-axis at 0. Does it touch or cross with odd multiplicity? You could flip back and look on the previous page if you needed to, but it says odd multiplicity means the graph crosses the x-axis there. I bet I know what was making a couple of you frown. I couldn't figure it out for a second, but was it because I didn't have the 2 there? Is that bothering anybody? If you set the x plus 2 equal to 0, or x plus 2 squared equal to 0, and take the square root of both sides, that's the same thing as just x plus 2 equals 0. So that's why I didn't write the exponent down. It doesn't give you an extra 0. What's the multiplicity of this 0? The exponent of that factor is 2. The fact that that 0 has even multiplicity tells me that the graph does what at that 0? Touches. Now, this much is monkey see, monkey do. Putting it on a graph takes a little bit of practice until you develop an intuition. Yes, sir. From setting x equal to 0 or x plus 2 equals 0. Gosh darn it. How far are you going to let me go before you tell me I wrote down something? I probably said 0 and -2 and wrote 0 and +2. Man, it's all going on iTunes U. It's like dancing naked on YouTube. Ugh. Okay. Not quite as bad as dancing naked on YouTube. Okay. As I was saying, this is monkey see, monkey do, as long as you're watching somebody who's doing it correctly. Graphing, putting this on a graph, just takes a little bit of practice. These zeros are my x-intercepts. Keep that in mind. By the B part, I know that the y-intercept is 0. I'll go ahead and plot that. By the C part, I know that 0 is an x-intercept, which I already have graphed, and -2 is an x-intercept. So I'll go ahead and plot that. Then attach your end behavior. I know what goes on the left end of the graph and the right end of the graph. All I don't know is what's going on in the middle here. Am I going to have my two little squiggles? I don't know yet. But I do know the graph goes down to the left of the leftmost intercept and up to the right of the rightmost intercept. All I've done is attach this end behavior to the left and right intercepts on the graph. The only thing to add in now is what happens at each intercept. What happens at -2? The graph does what? Touches, and touches means does not cross. Does a U-turn. What will this graph look like if it does a U-turn at -2? It's going to go back down. That's what U-turn means. We don't know how far it goes down. It may be just a little ways, or it may go way down there before it comes back up. This determining how low it goes takes calculus. That's one of the big things calculus is for. So you could just have your graph going down a little bit before it comes back up, but you don't really know how low it goes unless you know some calculus. It's kind of cool. Tells you what calculus is for. That's good enough. My graph had, hey, it had its two squiggles. Here's one turning point. Here's two turning points. And that's a pretty good graph of that function. Any questions? Anything else I've done wrong? Okay. All right. Y'all be nice to me. I'm getting old. Lady Clarol's coming to see me this weekend. Number 2. F of x equals -2 times x plus 4 times x minus 1 cubed. I don't want to have to multiply that all out. I don't want to multiply x plus 4 times x minus 1 times x minus 1 times x minus 1 to get it in descending order. All I need to say is if I did multiply that out, I'd have an x cubed along with a bunch of other stuff. And then that x cubed times this x to the first would mean that my highest exponent would be what? X cubed times x to the first. X to the fourth. 4, that's a 4th degree polynomial. Even degree, which means I know that both ends do the same thing. They either both go up or both go down. What tells me whether they both go up or both go down? The negative coefficient. What does this graph do on the ends? In which direction? Yeah, it's a concave down parabola looking graph, although it's not actually a parabola. You can connect those if you want to. The only reason I didn't connect mine is that I know it may have as many as how many squiggles in the middle? As many as 1 less than the degree or 3 squiggles in the middle. Courtney, is that okay now? You understand where we got that degree? Okay. All right. Okay, good. I'll have to share part of my salary there. All right, what about the y-intercept? How do I find a y-intercept? Nope, that's how I find x-intercepts. Find the y-intercept, I let x equal 0. All right, so I'd have y equals -2 times 0 plus 4 times 0 minus 1 cubed. This -1 cubed is -1. -1 times 4 is -4. -4 times -2 is -8. I'm sorry, positive. I caught that one myself. Positive 8. Negative 2 times negative 4 is positive 8. What are the zeros of this function? And this time, I'm not even going to make a side note. I can just look at these factors and see the zeros of that function are what? Negative 4 and positive 1. If you set negative 2 equal to 0, does that give you a solution? No, negative 2 doesn't equal 0 no matter what x is. But if you set x plus 4 equal to 0, that's where you get the negative 4. And if you set x minus 1 equal to 0, that's where you get the positive 1. I didn't ignore it. I paid attention to it and realized it didn't give me a solution. Never ignore it. But no, it just doesn't give you an x-intercept. What is the multiplicity of the zero, negative 4? The exponent of the factor x plus 4 is 1. So this is a big sentence you can use to impress people at parties. Negative 4 is a zero of multiplicity 1. That means the graph does what at negative 4? Odd multiplicity means it crosses. Yes. What is the multiplicity of the 0, 1? 3, because it's the exponent of that factor, which means the graph does what? That's also odd multiplicity, so the graph crosses at 1. That only goes into figuring out the end behavior. Then it's not a polynomial. That was part of the definition of a polynomial. It only has whole number or whole exponents or 0. It only has non-negative integers for exponents. All right, let's put it on the graph. I have 2 x-intercepts. What are the x-intercepts? Yeah, it's these zeros, negative 4 and positive 1. And the y-intercept is positive 8. That's way up here somewhere. And what is the graph doing to the left of the leftmost intercept, to the left of negative 4? Well, this is the left end behavior. The graph goes down to the left of that. What is the graph doing to the right of the rightmost intercept? It's going down as well. What does the graph do at each one of these x-intercepts? Crosses, so it's going to cross, keep going up. I don't know how high it's going to go. It's going to go at least to 8, but it may go on higher than that. There's no law saying the x-intercept has to be the highest point, or the y-intercept has to be the highest point. It could go beyond that before eventually it comes back down and looks like a concave down parabola. Yeah, I just wanted to show you you didn't have to. You can't assume that that's the highest point. Your chances of being struck by lightning are more than your chances of being eaten by a shark. Yep. All right, any questions on number 2? All right, number 3. What is the degree of that polynomial? Yep, because if you multiplied x minus 1 times x minus 1, you'd have an x squared. and then you'd have to multiply it by this other x, and you'd get an x cubed. The polynomial would be this long if you multiplied it out, but all I care about is the degree of the first term, so I just look at this x squared and that x to the first and say this is third degree with positive or negative coefficient. Coefficient's -1, so a negative coefficient. Does this mean that this graph basically looks like A, B, C, or D? Odd degree, negative coefficient, goes up on the left and down on the right. I don't know how many squiggles may be in the middle, but I know it's not going to be more than 2. How do I find an y-intercept? Let x be 0. Don't set it equal to 0. Let x be 0. -1 squared is +1 times 2 is -2. No, 1 squared is 1. 1 times 2 is 2. 2 times this -1 is -2. What are the zeros of this function? 1 and -2. That's from setting each factor equal to 0. What is the multiplicity of the 0, 1? 2, and what does that mean? The graph touches but does not cross the x-axis at 1. What is the multiplicity of the 0, -2? It's the exponent of that factor, which is 1, and that means the graph crosses the x-axis at -2. So here's what I know. I know the y-intercept is -2, and the x-intercepts are +1 and -2. What does this graph do to the left of the leftmost intercept? The left end goes up. What does the graph do to the right of the rightmost intercept? The right end goes down. All I need to do now is figure out if there's 1 or 2 squiggles in the middle. What does the graph do at -2? Oh, yeah, at -2 it crosses. It has to have this y-intercept. The graph may go on down below that. I really can't tell without calculus. I just know at some point it has to turn around, hit that y-intercept, and go back up to 1. What's the graph supposed to do at 1? And that's exactly what happens. Any questions? All right. I'm going to be very quiet, which is very difficult for me, and let you do number 4. All right. Most of my folks are looking up. Me too. On the first three examples, I wrote a bunch of stuff down because if I don't write it down, when you get home and look at your notes, you'll say, how'd you get that? You know, there's nothing written down. And on number 4, you wrote down stuff because I asked you to write it down, but I'm not going to write it down and show you how good of a grapher you've become, and I've become, just by knowing the stuff I'm supposed to know. I can look at that equation and tell you the x-intercepts are what? You can do that in your head. Set each factor equal to 0, and you get -4, +3. If you set x equal to 0, you do get a solution. See, if you set -2 equal to 0 right here, -2 doesn't equal 0 no matter what x is. But if you set x equal to 0, 0 is one of your x-intercepts. You just can't set a constant equal to 0. So this graph has 3 x-intercepts, -4, 0, +3. What about the y-intercept? I can do that in my head. If I let each x be 0, what would I get? -12 times 0, which is just 0. So the y-intercept, I already have it graphed. Well, let's see. What degree is this polynomial? If you multiplied all the x's together, you'd get an x to the fourth degree with positive or negative coefficient. Positive coefficient, fourth degree with positive coefficient means both ends do what? Go up like a concave up parabola. So just go up to the left of the leftmost intercept, up to the right of the rightmost intercept. Then look at each intercept left to right and say, what is the graph supposed to be doing at -4? The exponent of x plus 4 is 1, and that's odd, and that means the graph crosses the x-axis at -4. I don't know how far it goes down, but it crosses. And at some point, it has to turn and come back up. What does the graph do at 0? That even exponent of the x means the graph touches and does a U-turn. Yes? Boy, I hope not. I don't understand what isn't it positive unless you tell me what it is. Both ends go up. That's going up. You got it? Okay. And what did you say was going to happen at the origin? Even exponent means the graph touches, but does not cross. Does a U-turn there. This graph may be symmetric with respect to the origin. This hump of it's going to end up looking like a W. This hump of the W may be exactly as low as this one is, or it may go down farther. I don't actually know that without calculus. But at some point, the graph has to turn, come back up, and hit that other x-intercept. Just to double check, what should I know about that other x-intercept? What the graph does there? Looking at the multiplicity of this 0, it's 1. So this confirms, yes, my graph does cross at the last x-intercept. Mr. Kevin, what's making you frown? It's okay? Okay. So, with some practice, don't close up yet. So with some practice, you can graph these without writing anything down. if you graph it on the test without writing anything down. It's okay. That just tells me you've practiced enough to figure this out without a lot of work. It doesn't take a lot of work. All right. I want to check something. I know that this is Wednesday, so I see you again Monday. I know that Monday's lesson is really, really difficult to finish in one day, and I'm thinking about getting a little head start today. The only problem with that is I know most of you probably haven't printed the 5.3 notes, so I want to check something on momentum. I want to look at them and see if there's a lot you need to write on the very beginning of the sheet. I just don't want to leave 30 minutes early today and then end up not finishing what we're supposed to finish Monday. So let me check this on momentum real quickly. Oh, 5.5. Here's the other part of your homework. You do have assignment 13 on MyMathLab, and then you print this MyMathLab assignment 13 continued because MyMathLab just doesn't let you do great graphs with the mouse. All right, let me look at this 5.5 and see if I can. Well, you can write on it if you have it. I just don't want to start something that's going to be a big problem if you don't have the notes printed. I think we can talk about the first part of this without the notes printed. There are 4 examples, but you can write the 4 examples down. So forgive me for not anticipating that you needed the 5.5 notes, but I do want to go ahead and talk about them. Let me just switch gears here. We're only going to talk about the first little bit of this. So at most, you may have to write down 6 examples. You may also find that you can just listen and follow along without having to write a lot of it down. In 5.1, what we just finished, we graphed higher order polynomials. Now I can graph polynomials that are 5th degree or 7th degree or 99th degree, but I can only find the x-intercepts if it's given to me in factored form or if it's something I know how to factor. Some 3rd degree polynomials can be solved by grouping, group the first 2, group the last 2. But unless it can be solved by factoring, unless it'll factor some way that I already know how to factor, I'm going to have trouble setting the whole thing equal to 0 and finding the solutions. That's what 5.5 is about. How do you find x-intercepts of polynomial functions that won't factor using any factoring method we've ever learned? So it's only one additional step above what we've done today. It turns out that synthetic division is a great tool for finding the x-intercepts of a function that won't factor. And we talked about synthetic division in R.7, but that was a long time ago. So let's review it real quickly. I'm just going to write this down, and then I'll switch back to where you can see. All right. All right. Just write down these two examples, and let's make sure we remember how to do synthetic division. Some of you missed it on the first test, so we need to review. When you're doing long division, just like long division of real numbers in basic math, the steps are divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down, so there's nothing else to divide, multiply, and subtract to bring down. But one important step in long division is remembering that every time you go to subtract, you're distributing a -1. Most folks are lazy and just say change the signs, but that is lazy because nothing in math is hocus pocus. In synthetic division, we only have to change the sign once, and that takes care of, in long division, every time you multiply, you have to change the signs. Here's the one time you change the signs. You take the opposite of that constant in the denominator and put it in a little box that looks like that. Make sure you're taking the opposite because that's taking care of that very important step of subtracting in long division. Then out beside that box, you put the coefficients of the numerator. Make sure that the numerator's in descending order and see if it's missing any terms. By that I mean I have a third degree term, a second degree term, a first degree term, and a constant. So this numerator's not missing anything. This one is. I'm missing an x squared. I'll deal with it when I get down there. But this one's not missing anything, so the coefficients are 1, 1, -8, and -17. And then skip one line on your paper. Draw a long horizontal line. Yes, you have got to be kidding. Okay, I believe you. I believe you. It is 2x squared. I just have already had my quota of mistakes for the day. I wasn't allowed anymore. That is on the handout 2x squared, so that second coefficient should be 2. Draw a long horizontal line, bring that first number straight down under the line. The reason you can bring that first number straight down is if you're dividing the leading coefficient by the bottom coefficient, 1, you're going to get the same thing. If this was 2x cubed divided by 1x, the first coefficient would still be 2. So you always bring that first coefficient straight down and then start the process of multiply, add till you run out of stuff to multiply and add. You multiply what's in the box times what's on the bottom row. 3 times 1 is 3. You put that under your next coefficient and then add. Then multiply what's in the box times what's on the bottom row. 3 times 5 is 15. Put that under your next coefficient and then add. -8 plus 15 is 7. Then multiply what's in the box times what's on the bottom row. 3 times 7 is 21. Put that under the next coefficient and add. -17 plus 21 is 4. Now my answer is not 1574, but those are the coefficients of my answer. If I'm dividing an x into an x cubed, what power will I start out with? An x squared. This 1 is the coefficient of x squared. And after that, the terms are in descending order. So that 5 is the coefficient of x to the first. That 7, well, the next lowest exponent would be 0, or just that term has no x, it's my constant. Since I've run out of powers of x, what must this last number be? That's my remainder. X squared plus 5x plus 7 is called my quotient, and 4 is my remainder. Now, in basic math, if you say 15 divided by 6, 6 goes into 15 2 times with 3 left over, how do you check that? You multiply your quotient times your divisor, and then add the remainder. 2 times 6 is 12, then add the 3 and you get 15. Same thing should work in algebra. If I multiply the divisor, which was x minus 3, times the quotient I found, x squared plus 5x plus 7, it would take a few minutes to multiply that out, but I could do it. I know how. If I multiplied that out and then added 4, it would give me back the numerator I started with. I don't have time to prove it, but, at the party tomorrow, you could multiply x minus 3 times x squared plus 5x plus 7, and then add back your 4, and you'd get what you started with. And you'd get an extra s'more. Oh, me either. I think melty marshmallows are gross. All right, example 2. Practice this one more time, because what I've done on the handout, when you print it, now that we've reviewed synthetic division, the rest of the problems we do, I've already done the synthetic division, just allow us to go more quickly in class. So we're reviewing it so that you know how to do it, but then the next many examples, I've already typed the synthetic division. All right, what goes in the box for example 2? Positive 1. And then out beside that box, the coefficients of the numerator, and what's missing? X squared. What could I put in place of the x squared that really wouldn't change the value of the numerator? 0. You could put in a 0x squared, and if you forget to, you're not going to get the right answer. The coefficients are 3, 0, negative 4, and 2. Somebody's pacemaker going off? Everybody's too embarrassed to check. Okay, 3, 2, 1, 0. I've got all my terms. Y'all go ahead and do the synthetic division just for practice. Is that what you got on your bottom row? What does that mean my quotient is? I divide an x cubed by an x to the first, I'm going to start out with an x squared. So 3 is the coefficient of x squared. 3x squared plus 3x minus 1, and then the remainder is 1. Which means if I wanted to check this answer, I could write that numerator as the divisor. The divisor was x minus 1. Times the quotient. Plus the remainder. If I multiplied x minus 1 times 3x cubed plus 3x minus 1, and then added that remainder, I'd get back the original polynomial we started with. Yes, ma'am. I quit. I am not coming back. Okay, what just happened? 3x cubed plus 3x squared. I left out the remainder. That's 3x cubed plus 3x squared minus x. No. Oh, 3x squared. Did I say x squared and write cubed earlier? I bet I did. I think I've said it right. I think every mistake I've made today, I've said. Yeah. Wonder what kind of dyslexia that is. I think I'm having mini strokes. Yeah, 3x squared plus 3x minus 1 plus the remainder. See, I even have it written right here. It's good? Okay, let me tell you one more thing. You don't have to write anything else down. We have the first 2 examples on the notes done, and that's going to help us get through with the material Monday. But let me just what if for a second. What if I divided 2 numbers in basic math and I got 0 remainder? What would that tell me? 6 goes into 18 evenly. Or what do you call a number that goes into another number evenly? It's a factor. If you get 0 remainder, then your divisor is a factor of the numerator. Those of you slamming books are missing good stuff, right? So algebraically speaking, if we divided this polynomial by x minus 1 and we didn't get a remainder, that would mean x minus 1 is a factor, and all of a sudden we would have factored something that we could not have factored before. That's so exciting, it gives me chill bumps to be able to factor something I've never factored before. That's what 5.5 is about, factoring by synthetic division, things that we could not factor any other way. All right, y'all forgive me for my errors today. Thank you. I don't know what I would have done if you refused.